we're going to consider how to solve non-homogeneous linear DEs, so of this generic form Ly equals f of t. So as a very simple example, let's talk about a first order constant coefficient linear DE. This one's non-homogeneous. Now we know what to do. We've talked about the integrating factor before. Now when you've got the integrating factor, essentially you're figuring out a magical function that you can take, you can multiply on both sides of the differential equation, this first order linear problem. And when you do that, the property of this integrating factor is that it will always turn the left-hand side into a perfect derivative. And because it's a perfect derivative, you can now integrate. And you can find the antiderivative, the most general antiderivative that you can for this expression. And you'll get this arbitrary constant c. Now this allows you to come up with two parts to the solution. You'll have ce to the minus at plus e to the minus at, and then you'll have an antiderivative here, e to the at f of t dt. This part I'm going to call yh for the homogeneous, and this part I'm going to call yp. So if I took the homogeneous differential equation and I just let y equal e to the lambda t, that I'll end up with lambda plus a is 0, so lambda would be negative a, and that's exactly what I'm seeing right here. So the homogeneous solution is the solution to the homogeneous problem that's connected to this differential equation. This deals with the left-hand side of the differential equation. And the right-hand side of the differential equation enters into this story when we talk about f of t. That was the function that was on the right-hand side. So this yp is called a particular solution. So this is the part that solves Ly equals f. Now, in general, this is going to be true for any Ly equals f, any order linear DE, that the full general solution will always be the part that comes from solving the homogeneous, so the associated Ly equals 0, plus a part that comes from dealing with the right-hand side, something that we call the particular solution. So this part deals with the right-hand side. And this is theorem 2.5.1 in the text. But this is an important result. Now, you should think of this like linear algebra. When you've got ax equals b, your solution always had a homogeneous part, the part that was related to ax equals 0, as well as the part that was dealing with the right-hand side, dealing with the b portion of it. We say, well, how do we solve Ly equals f? First step is you're going to solve the homogeneous equation, Ly equals 0, and that will get you this yh. And then you need a method to deal with the right-hand side, the thing that we're calling f. So two common ways. One of them is called the method of undetermined coefficients, and that's what we're going to talk about in this series of videos. And then another one that's more slick is something that I'm going to call a Green's function method, and your textbook will call variation of parameters. In undetermined coefficients, there's a basic idea. If I give you a non-homogeneous differential equation, there is some right-hand side that we're going to call a driving force. The particular solution is kind of like the response of the system. We're going to say that it's proportional to the driving force. So if you drive it with a constant force, it's going to respond with a constant force. What we're saying is if our right-hand side is the solution function for some linear constant coefficient problem, then yp will just be related to that function. So the kinds of functions that we need to deal with here on the right-hand side are going to be polynomials. So if we ever see some polynomials kind of like this, these are all possible solutions of constant coefficient problems. Those will work. Exponentials, e to the at, sines, cosines, those will work. These strange combinations of sines and cosines, those will work as well because they were all possible solutions of constant coefficient problems. Anything where you put a multiple in front of all of them, all of those ideas will work. So if your right-hand side, if your driving force is a function that comes from solving some other constant coefficient linear problem, then this idea will work. So let's actually dive into this method by showing you some examples. So first of all, let's talk about this second order constant coefficient problem. The first thing we need to do is talk about the homogeneous solution. Y double prime plus y is 0. We know that we should have e to the lambda t as our guesses. And when we plug this in, we're going to get a quadratic equation that looks like this. It's very straightforward to solve. Lambda is 0 and lambda is -1. So that means that the homogeneous solution would be c1 e to the 0 plus c2 e to the minus t, or better yet, c1 plus c2 e to the minus t. Our fundamental set to this problem is 1 e to the minus t. So now what I'm going to start to do is give you some different driving forces. So if the driving force is 7 e to the t, the whole idea behind this method is to try a particular solution as a guess. You're going to say, oh, it's proportional to the driving force. So if I'm driving it with an e to the t, then I'm going to try some unknown, undetermined multiple of that, a e to the t. I'm going to take the derivatives, and then I'm going to substitute them into the differential equation to try to figure out what a is. So if I put this into the dE, this is going to give me an equation for a. I'll have a e to the t plus a e to the t is 7 e to the t. This is going to tell me that 2a e to the t is 7 e to the t. So you can clearly see that a should be 7 over 2. And that means that the particular solution would be 7 over 2 e to the t. The general solution would then be a combination of the homogeneous part and the particular part. So it would be c1, c2 e to the minus t plus 7 halves e to the t. Now, I'll note that if you are given initial conditions, you have to apply it to the full sum, yh plus yp. So as an example there, let's say I gave you that differential equation, and I also told you that y of 0 was 0 and y prime of 0 was equal to 1. So if I gave you those initial conditions, y of t, the full solution, would be c1 plus c2 e to the minus t, 7 halves e to the t. Y prime would be negative c2 e to the negative t plus 7 halves e to the t. If I apply the initial conditions, I'll get c1 plus c2 plus 7 halves is 0, and I'll get that negative c2 plus 7 halves has to be 1. So c over 2 is going to be 7 over 2 minus 1 is 5 over 2. And then if I reorganize this for c1, I'll end up getting that c1 is negative 6. The unique solution to the initial value problem would then be negative 6 plus 5 halves e to the minus t plus 7 halves e to the t. So in principle, the idea is straightforward. However, so if I just make a small tweak on the right-hand side, so if I were to say, okay, here the right-hand side, the driving force is 7 e to the minus t, if I were to try that the particular solution is a response of that, just a mirror image of that, if I go through and I do the same old stuff that I just did a moment ago, I'm going to run into a problem. And the problem that I'm going to run into is that when I substitute everything in, here's what I get. 0 equals 7 e to the minus t. This is what we call a contradiction. I have no way of figuring out what A is here. So something went wrong. And the whole problem here is that this guess, particular solution, is actually part of the fundamental set for the homogeneous equation. I have no chance of this particular solution giving any non-zero right-hand side when I put it into the DE. Right? If I were to put this into the DE, it's always going to give me a 0. There's no hope. It's a homogeneous solution. That's what homogeneous solutions do. And so now I need another function for yp that is independent of the fundamental set. As we are going to try at e to the minus t. So we're going to put in this linear factor because that will make the particular solution different, linearly independent from our homogeneous set. And so I'm going to take that function, take its derivative, and when I go ahead and I take its derivative, I got a little bit of work to do because now I need to use the product rule. But it isn't horribly bad to do it. You just have to go through and hammer out everything. So if I were to go ahead and do this, and I sub it into the DE, I'm going to get negative 2a e to the minus t plus at e to the minus t plus a, so this is y double prime, plus a e to the minus t minus at e to the minus t. This would be 7 e to the minus t. So when I go ahead and I do that, these very conveniently go away. That's great because there is no term over here on the other side that has t e to the minus t. So I need those to go away. What I'm going to be left with is negative a e to the minus t is 7 e to the minus t. And that tells me that a is going to be negative 7. So I have correctly found that the particular solution is negative 7t e to the minus t. The general solution is always made up of the parts that deal with the left-hand side, the homogeneous terms, but now I have this right-hand side contribution from the particular solution. If we were to say, oh, the right-hand side is a constant, if we were just to try the particular solution as a constant, all of its derivatives are 0. If I were to plug it into the DE, I would get that 0 is 7, which is a contradiction. Once again, yp equals a is part of the fundamental set. Remember the fundamental set had 1 and e to the negative t? That 1 consists of every function that's a constant. I have to bump it up 1 degree. And when you deal with polynomials, you should be sure to make them as general as possible. If I take its derivative, I'll get a. If I take the second derivative, I'll get 0. And if I sub that into the DE, I'll get a 0 plus a has to be 7. So that means a is 7. And b is unknown. Okay, so how do I interpret this? There's the homogeneous solution. This b gets to be absorbed into there. So then all we would identify as the particular solution is just the remaining term. The particular solution here would be 7t. And finally, if you were to try that again, let's say with the right-hand side being 7t, you would find very naturally, you'd say, oh, I'm going to try the particular solution as at plus b. And if I were to take the derivative, I'd get an a, and the second derivative, I would get a 0. If you were to sub that in, you would find a contradiction again. 0 plus a is 7t. This is a contradiction. So the lesson here is that any time contradictions arise, you should increase the degree of t in your particular solution. So here I would try the particular solution is at squared plus bt plus c. The first derivative would be 2at plus b. The second derivative would be 2a. You plug all that in, 2a plus 2atb equals the right-hand side of 7. You would find a system. 2a plus b is 0 because there's a constant over on that side. Constant and constant equal this constant. And then the other equation would be for powers of t. And you would have that 2a is 7. So here you'd find that a is 7 over 2. And then in the other equation, you would find that b is negative 7. The particular solution would then be 7 over 2t squared minus 7t, and then this c was not determined. But remember, the fundamental set is just going to absorb this. And then we would just therefore classify this as the particular solution. So the method of undetermined coefficients is about guessing and checking. If you run into problems, bump up the power of t.